In the last screencast, we introduced angular momentum as observed in an inertial reference frame, and then began to develop some intuition about what this actually means. And so the expression itself is the position vector crossed with the linear momentum vector. And so this does resemble the position vector crossed with a force, which is the moment. And also mentioned there in the last screencast that this is another name for this when using an inertially fixed point is called the moment of momentum. And so far we haven't actually used a real moment. But the great part about angular momentum is that it is related to a moment, which is r cross f, the expression that we typically think of. So let's take a look at how that works. Let's take the time derivative of this entire expression as observed in the inertial reference frame, which means that we distribute that time derivative to both sides. We'll leave our left-hand side alone and just leave it as the time derivative as observed in the inertial reference frame of the angular momentum of p with respect to O as observed in the inertial reference frame. And so for our time derivative on the right-hand side, we'll distribute this. And so we see using the product rule, we get the time derivative of the position vector crossed with the mass times the velocity, then plus the position vector crossed with the time derivative of the velocity. And then we see that for the first expression, the time derivative of the position vector is the velocity of p with respect to O as observed in the inertial reference frame. And then when we take the cross product of the velocity and the velocity, we get the first term is equal to 0. And then examining the last term, it's r cross the time derivative of the velocity of p with respect to O as observed in the inertial reference frame. And so that time derivative is equal to the acceleration of p with respect to O as observed in the inertial reference frame. And so then our cross product that we bring down is r of p with respect to O cross with the mass p multiplied times the acceleration of p with respect to O as observed in the inertial reference frame. And so we can simplify this expression even further by recognizing that it's a mass multiplied times the acceleration. And the acceleration is in the inertial reference frame, which means that this is the right-hand side of Newton's second law. So the mass times acceleration is equal to the sum of the forces all on point P. And so now that we have this cross product, r of p with respect to O, crossed with the sum of forces on point P, this is something you should recognize. And this is equal to the moment due to all the forces on point P with respect to point O, or about point O. So let's take a closer look at this expression. And so what we have is the time derivative as observed in the inertial reference frame is of the angular momentum of P with respect to point O as observed in the inertial reference frame. And this is where O is an inertially fixed point. This is equal to the moment of all the forces on P about point O, or with respect to point O. And this expression is only good when the point that all this is being taken with respect to is fixed in the inertial reference frame. Now the value of having this expression is that we can use this to calculate equations of motion. And the reason why is because this is no different than Newton's second law, but it's in a rotational form now. So it's the same thing as F equals ma. F equals ma is actually buried in this expression. But now if you have a rotational system and you have an inertially fixed point, you can use this formula in which you calculate the angular momentum, take the time derivative of the angular momentum, and then set that equal to the moment due to all the forces that are acting on point P, and then now you'll get an equation of motion out of it. And this will be something that we tackle in the next screencast of developing equations of motion on a rotational system with this expression. Let's finish up this screencast by looking at an important part of this expression of Newton's second law, and that's when we have the conservation of angular momentum. So this is when the total moment acting on a particle relative to the point O is 0. The inertial angular momentum of the particle relative to O is constant or conserved. Conservation of angular momentum, when it exists, is a helpful thing to recognize as quickly as possible, because if you can look at all the forces that are acting on a system and determine that the moment about a particular point is going to be 0, then calculating the dynamics of the system become pretty easy to do. And it also gives you an indication about how the dynamics work, how the equations of motion in that rotational system are going to act. Now, a couple of examples in which you'll recognize that angular momentum is conserved would be like a figure skater. And let me say the figure skater is spinning around, and when they have their arms out, you recall that when they spin at a particular rate. And then as they pull their arms in close to them, they spin much faster. No matter what, though, in that system, angular momentum is conserved the entire time, even though the speed changes. Another example that you recognize is when we have what's called big gravity. So we've got a big planet with a big mass m, and then let's say we've got something like a star, or I'm sorry, a moon, or maybe a satellite, and then there's a gravitational attraction between the two. And so this gravitational attraction is what's called a central force, meaning that the forces that are act in line or through the center of both of those objects. And so you can see that there's no moment that's being caused to create this orbital motion. And so in orbital motion, we have a conservation of angular momentum, even though the velocity is changing as the planet or as the satellite rotates around the larger mass. And we'll deal with that a couple topics in the future.